right, you should be able to see my screen shortly. So we got to talk about the conditions that cause current to arise in a conductor, and we spent a bit of time talking about about a simple circuit that had essentially no resistance except for the internal resistance or the natural resistance in this conducting wire. But we just imagined that we had a charged capacitor in place of our battery, and we took a look at what had to be happening on the exterior of a wire in order for a current to arise on the interior of a wire. And let me get this little thing out of the way. There we go. Oh, give me a second. All right. So we talked about the concept of electron current, and we got to line that up or compare it to conventional current near the end of our last lecture on Wednesday. For the concept of electron current, we are acknowledging that in reality, the positive ions that make up the interior of the conductors that we're working with, they're not actually legitimately free to move through the interior of that material, whereas the sea of electrons, the ones that are not so tightly bound to the positively charged nucleus, they are free to kind of wander, and they can respond to shifts in electric field. So if we are looking at just the concept of electron current, we just care about the number of particles that pass through a certain section of a circuit per unit time. And as we saw, you can kind of maximize the number of available electrons by selecting a material that's got a large electron density. So this kind of backs up the idea of, or the practical reason why copper wiring is so, I guess, valuable from a design perspective, because you can maximize the number of available electrons that are already present in that wire, and thus the amount of both time and distance that you would have to wait for one charge to bump into another is minimized. And when I refer to that, I'm referring to the concept of, well, I'm referring to something that we saw kind of illustrated a little bit later on. So like right around here. So we know that in reality, it's not appropriate to think of a current carrying wire as something that's hollow and that can allow the flow of charge the way that an empty hose or a straw can allow the flow of liquid. In reality, this wire is already filled with electrons. So if we go back and take a look at that very, very low, very slow looking drift velocity, it might seem like you would need to wait a very long amount of time, so a matter of minutes, to figure or to actually observe a light, let's say, switching on after you turn a switch. But in reality, since we're just waiting for one particle to collide with another, the effect of that changing external electric field or that changing external charge distribution registers almost immediately. And it's not exactly immediately, but it's on the order of nanoseconds. So if you think about what's going on in the interior of the wire, if the charges that are actually doing the moving are negatives, and they are going from being at rest to not being at rest, then there has to be some internal electric field that's causing those charges to move. And that internal electric field is the result of some external charge distribution that is non-uniform. So in this case here, if we have a charged capacitor and we connect these two wire segments to the plates, but we don't let them touch, these charges are going to arrange themselves as far apart from their nearest neighbors as they can achieve. And then once that's done, they are static. They're not just freely moving anymore. So if we could subdivide, if we can cut into this wire, then we would find that the electric field on the interior of the wire was also equal to 0. So the interior electric field is completely dependent on the exterior charge distribution. And as soon as you connect that little gap, now these electrons that started off on the negatively charged plate can get even further away. because now they have access to the other half of the circuit that they couldn't access beforehand. And in the time that it takes for these charges to rearrange themselves, the field on the interior of the current carrying wire is no longer zero. So it's capable of exerting forces on the charge carriers that exist inside that wire. And regardless of which end of the wire is connected to or which plate of your charged capacitor, the net electric field is going to have a consistent direction. So that means that any negative charge that was already on or in the interior of this current carrying wire, it would be subject to a force that's directed toward the left side of our screen, because we know that the net field is directed toward the right. So the force that a negative charge would feel would be anti-parallel to that. So let's see, we did a couple of thought questions. We talked about the difference in the trajectory of a particle that is moving through a conductor that has no interior electric field compared to one that has some non-zero interior electric field. And the result is that now there is a downhill direction, or there is a direction that charges will tend to drift. That's not really present when you have zero exterior field. Excuse me, I meant to say interior, zero interior field. So in the case where the field is not present, we can model these electrons as if they're undergoing perfectly elastic collisions with each other or with the positive ions that make up the lattice of the material. And these particles are still capable of undergoing elastic collisions, but now they're subject to another force. We can sort of think of this as being kind of similar to projectile motion, in that if we could switch gravity off and just fire a projectile horizontally, then we would find that both the horizontal velocity and the vertical velocity would remain consistent. So we would have a straight line trajectory instead of the parabola that we actually observe, since there is an unbalanced force in the y direction for a projectile. So instead, these trajectories are more parabolic. However, if we were to measure the if we were to measure the net displacement that a particle undergoes, we would get something that's non-zero in this case, as opposed to something that's essentially zero here, because every little segment of this trajectory that I can find that has a positive velocity, there's absolutely nothing precluding me from finding a similar one that's got a negative velocity. So when you sum those together, you get a net displacement of zero when there's no interior field, but that the presence of that electric force that is indicated by the electric field vectors here means that there's a downward direction, or that there's a trend. We talked about the mean time between collisions, but I would like to jump back over to this half, so the second half of our current and resistance chapter, and I'm just waiting for this little toolbar to get out of the way so I can access the stuff it's covering up. But until then, the electron current and conventional current are opposites. So conventional current allows us to imagine a scenario where the positives legitimately are moving through the circuit. So if you know the direction of the electron current, you know the direction of the conventional current by default. And instead of just tracking an individual charge carrier that's moving past or through a certain section of a circuit, we are now looking at some differential portion of a larger, like macroscopic charge, capital Q. So the first derivative of charge with respect to time is something that we can interpret as the conventional current. So we ran into the amp for the first time. That's just charge per unit time, another combination of fundamental units. The fundamental units in the SI system being kilograms, meters, seconds, and then coulombs, which is one that we did ignore for the entirety of semester one. Let's see, we talked about the concept of current density and what that means in terms of like internal properties compared to external ones. So the lab that we did last week is kind of a perfect example. We were able to directly measure the physical size of the tube that we use to hold our saltwater solution. And if we connected an ammeter in series with that tube, we could get a direct measurement of the current in that tube. What was a little more opaque, or what would have been more difficult to evaluate, is the number of electrons that are freely moving through that solution at any one point in time. And I don't recall whether it's stated outright in the text of the lab, but the benefit to adding a larger amount of salt to the solution is that you are introducing a large number, or a greater number, of negative ions. So the chlorine that's a part of the sodium chlorine molecule, that has the effect of boosting this electron density N sub E. So if you have more of those electrons to go around, but they're all traveling at about the same speed, because they're all subject to an electric field of the same strength on the interior of the tube, then that should increase the current density. That's what you should have observed in your data tables from last week. So we went through a couple of these, but what we were also able to evaluate is at least in the lab, we were able to draw a parallel between the electric field strength, the current density, and then sigma being the conductivity of the material. So before I get too far out of sequence there, we were introduced to the second of Kirchhoff's circuit laws. The first one that we encountered was in our potential and field chapter right before our exam. And we determined that if we had a charge carrier, that we could move through some space that was affected by an electric field. As long as that charge carrier made a closed loop, it could be a very long convoluted path, or it can be a smaller, more economical one, but the sum of the potential differences had to be equal to 0. Here, instead of focusing on really the field that is responsible for causing our charge carrier to move, if we look at the charge carriers themselves, then we can use the law of conservation of current, which is just kind of stated in equation form here, to account for all of the charge carriers that go into some junction, and thus we can account for all of them that have to come out. So there's no way for a charge carrier that heads into this input, into the input side of this junction, there's no other option that this charge can have aside from the paths that are shown here. And when we combine that law with Ohm's law, we can use that to solve the simplest type of circuit all the way up to the more complex ones that we're gonna, at the very least, get to the simple ones today. We may or may not get a taste of the more complex ones by the time our 2 hours are up. So we know that current density is something that we can evaluate by taking some kind of external measurements if we know the size and shape of a conductor. However, we also can track current density in terms of the conductivity of the material and then the electric field strength acting on it. So this J is exactly the same as the one that we saw a few slides earlier, where this conductivity has a unit that is maybe not introduced in the slides here, but it's got a unit that is a little interesting. It is inverse ohm meters, where an ohm is the ratio of a volt and an amp. So we can find the conductivity of a material if we know, let's say, what it's made out of, if we know the mean time between collisions, which is this tau, and then once again, we have this embedded charge to mass ratio, an E over M. The same way that insulators are kind of like the opposite of a conductor, conductivity's opposite is resistivity. So the greater the resistivity, the more that material opposes the flow of electrons through its interior. And we can say something opposite about conductivity. A high sigma material is one that does not kind of strongly impede the flow of charges through its interior. So I recall us doing these thought questions here. We talked a little bit about superconductivity, But this is the new part of our conversation here. So I mentioned that if you pair those, the Kirchhoff, or if we pair Kirchhoff's circuit laws, the loop law and the junction law, with another relationship, we can use that to gain insight about really all aspects of a simple circuit. And we didn't do this in the setup that we had last week. We're going to get some hands-on experience with that in this week's lab. But we could have determined what the resistance of the tubes that we, or the, I guess the resistors that we made out of tubes and liquid. There's a resistance value that we could have determined for those materials based on, and it would just be based on the length of the conductor. So if we're thinking about our standard tube, where L was the same for all 6 cases, then the only thing that could impact the resistance of that tube is the conductivity. Sigma was different. But you noticed, I'm sure, when you were increasing the potential difference across the sides of your saltwater tube, the electric field strength was staying the same because you weren't increasing and I should say for like a specific delta V. So for like 1 volt, let's say, it didn't matter which material or which liquid you had in the tube, you were getting about the same electric field strength each time. But what did matter was the number of available negative charge carriers that were in that tube, and then 2, the amount of, I guess you can sort of think of it as the net force that's acting on any one of those charge carriers. So there's a force that comes from the field that's causing the charge carriers to move in a certain direction, but there's also a resistive force, so almost like a frictional force that opposes that. But in all cases, the frictional force was not big enough to counteract the force that comes from the field. So we could determine that the net force was not equal to 0, and we could figure out which direction it was. So when you change liquids, you were really just changing sigma, which is the reciprocal of rho down here. So we could go back to our data set from last week and gain some more insight about the resistance of each of those individual tubes. We know from our earlier discussion of electric field strength that if we can measure the potential difference between any 2 points in space and take the ratio of that displacement that a charge carrier would have to undergo, that's effectively exactly the same as taking the first derivative of the potential with respect to position. And here, there is no negative sign that showed up when we were talking about the relationship between potential and field back in Unit 2. And the reason why that is not showing up here, or it's not, I don't want to say it's not relevant to the conversation, but what we're not doing here is trying to examine this scenario from an energy conservation standpoint. And that -1 that showed up when we were going from electric field to electric potential, or the other way around, was a result of that factor of -1 difference between the change in potential energy that our charge carrier was experiencing and the amount of work that the field would have to do in order to achieve that charge carrier, to achieve that displacement. So as long as we can get a direct measurement of delta V and we know the separation between our 2 points, that ratio is going to be the electric field strength. And it would just kind of be up to us to determine whether our electric field vectors point in the direction of the positive axis, which is essentially what's indicated here. Just in general, we say that positive increases toward the right, so we could treat these electric field vectors as being positives. But if we could reverse, let's say, the direction of the delta V here, let's say that the potential on the left side of this wire was more negative this time, and on the right side it's more positive, I wouldn't be able to change this field strength without changing the delta V or changing the material that the wire is made out of. All I would do is change the direction of those electric field vectors, but the strength would stay consistent. That's why we can ignore the negative right here. So this is exactly what we did last week in lab to figure out the electric field strength. You had a delta V that you controlled with your power supply. You had an L that you measured, that was the distance between the contacts, and we found that when delta V went up, E went up. As far as current density, it might not have been immediately obvious before you started collecting data, but the current density is something that changed based on the current values. So in other words, if we imagine we're still talking about our standard length tube, there's nothing we can do to change the length or the cross-sectional area. But you did notice that when delta V was larger, the electric field was stronger, and the current that you measured in the tube was also greater. So that means that if I increases, but the cross-sectional area does not increase, the current density is going to go up. But nothing that you did to that liquid changed its conductivity value. So sigma and thus its reciprocal rho, those were constants that were just fully dependent on the electric field strength. So and I should say the sigma and rho being constants meant that the current density was completely dependent on the electric field strength, just to make that clear. So if we solve these two equations simultaneously, we can predict what the current should be based on a whole bunch of constants, A, rho, and L, and then our one variable, delta V. So here's that same relationship again. If we interpret, I feel like we're jumping the gun a little bit here, but if we take a look at this relationship up here at the top, I have current on one side, I have delta V on another, and a whole bunch of constants here. And when we take a look at Ohm's law in a few moments, Ohm's law is going to relate current, voltage, or potential difference, and then we can interpret that group of constants as the resistance of our wire. And in the language here, we're talking more about like a real circuit, something that you could build not out of wires and plastic tubes and salt water, but just wires, resistance elements. They could be light bulbs, they can be inductors, they can be capacitors, but for either a section of wire or a traditional resistor, the resistance value increases as the length increases, it increases as resistivity increases, and it decreases as 1 over the cross-sectional area. So this was at the very bottom of our whiteboard last week, and we really didn't need to think about this particular relationship until we got to the ranking problems at the end. But we have enough data to gain some insight about the resistance of the tubes that we worked with. And you probably, even before this lecture started today, you probably had a pretty good idea of how the resistance, even though we weren't really calling it by that name, you probably have a good idea of how this R value changes in response to delta V. Or I should say, as this R value does not change in response to delta V, but the current that you can achieve through any one of those tubes does change in response to delta V. So let's look at this relationship here, because I feel like that is explaining the same thing, but maybe in a less clunky way. If resistance is the resistivity times the length divided by the cross-sectional area, then we can take the group of constants that we saw on our previous slide up here at the top, and we can just we can take the reciprocal of those constants, and we see that I is equal to 1 over the resistance times delta V. And that's how we got this value here. And this relationship here, and this is Ohm's law. This is going to be incredibly useful to us over the next 2 chapters specifically, but it's going to show up throughout the entirety of Unit 3. If you have 2 observable, or I should say easily observable quantities, so the current is something that we read off of a meter last week, and delta V was the same, we could determine the resistance without needing to know the conductivity of our liquid, without needing to measure the tube to get its length or its cross-sectional area. We could just look at how voltage, current, and resistance relate to one another. So this is another way that we can evaluate current that does not require that we know the total amount of charge that goes through the tube, because that is something that we weren't able to easily measure. We couldn't figure out, let's say, the total amount of charge carriers or the total number of electrons that pass through, let's say, the absolute center point of our tube. That is something that we could infer because we had 2 measurable quantities. But this, I guess this I always tend to think about this in terms of internal properties compared to external. So this is like our external view of what current means or how we can quantify it. If we can take two measurements, so delta V and R, where for most resistors, for ohmic resistors, R is a constant all the time, but there are some resistors for which R changes in response to the amount of current that's moving through the resistor. We're going to see that coming up a little bit. But except for those cases there, R is a constant. So if you can measure V, you can gain insight about I. If you can measure I, you can gain insight about delta V. And if you don't know the resistance, which was our case last week, you could take these two measurable quantities, like our external quantities, and figure out what the resistance has to be. So to relate this back to our earlier, our escalator model, so that we can kind of get a sense for how the energy of a charge carrier on the interior of a battery changes and how we can basically exploit that change in energy to power a simple circuit like this. So imagine that we could break this apart and put maybe a light bulb somewhere in this loop. We know that the imaginary escalator is going to stay on. So because there's, when we were first looking at this, we were relating it to, or we were thinking about how to use a battery to charge a capacitor. And we knew that the escalator would kind of switch itself off once the capacitor was fully charged, because a charge carrier couldn't literally jump from one plate to the next and make it through the remaining half of the circuit. But there is a gap that prevented that. In the absence of this escalator is always on. So a positive charge that we're imagining climbing this escalator is going to have some positive work done on it so that its potential energy, and it's electric potential energy, but we can sort of relate this to what happens when any object gets further away from Earth's surface. It's gaining potential energy of some sort. So when that charge carrier gains potential energy, now once it's actually to the top of the staircase or the top of the escalator, it's got potential energy that it can lose as it's making its way through this circuit. So you start off with some total amount of potential energy. So for an electron, so the thing that's actually responsible for the current that we would measure in this wire, this would not just be any old generic Q, but the fundamental charge times delta V for whatever the battery is. And then the magnitude of that potential energy would get smaller and smaller and smaller as we work our way down to the negative terminal. So it's ready to hop back onto the escalator so it can be lifted up once again, and then it can lose all of that energy. So I mentioned that we could imagine putting a light bulb or some resistor inside of this circuit so that now the act of moving through the wires is not the only place that our charge carrier can lose potential energy. And this is exactly what happens in a simple light bulb circuit. The energy, the potential energy that our charge carrier gains after it moves up the imaginary escalator, some of it is going to be turned into motion because our charge carriers are actually moving. So there's some kinetic energy to account for. But as soon as that charge carrier goes into, let's say, a light bulb, we want to use that as our example, it's going to lose energy, lose some of that potential energy as both radiant energy and heat. And that is going to deplete, or it's going to kind of rob this charge carrier of energy faster than this charge carrier would lose energy if we just had this simple battery wire circuit, which in real life would cause this battery to short circuit for reasons that we're going to talk about, I think, later on, probably later on in today's lecture. But my long-winded point here is that if we wanted to figure out what the current in this wire is, it would depend on the amount of charge that's moving through any one point of that wire or any one point of that circuit per unit time. So just as the light bulb in my hypothetical scenario a moment ago, just as that light bulb ultimately takes potential energy away from a charge carrier at a fairly rapid rate, exactly the same thing is happening inside the wire itself. So if I could take a voltmeter and put it not directly on the positive or negative terminals, but just, let's say, 1 millimeter above and below each of those. I would be measuring the potential difference for the wire itself. And that delta V for the wire should be the same as delta V for the battery. So this kind of gives me two different ways that I can think about the current that is present in this circuit. From one perspective, if I take the ratio of delta V of the battery over the total resistance in this circuit, this is telling me how much current the battery has to produce. You can sort of interpret that as the speed of the imaginary escalator. If I only have, let's say, these 6 positive charges that I'm imagining are moving through the circuit, and I can't add or subtract anymore, then if I cause those 6 charges to move quickly, I'm going to be pushing a greater amount of charge past a certain point in a circuit per unit time. So that would be a large current. So that would be like the escalator running at a high speed. But if I could turn that down so that I'm still working with the same amount of charge, but it's moving through this loop at a smaller rate, then that's something I can interpret as a smaller current, even though I haven't added or subtracted any charge carriers. So if that is the way that we can think about the current that the battery is responsible for introducing to the circuit, then this ratio here, delta V across the wires divided by the resistance of the wire, that should also be equal to the same current that the battery produced. And I should point out here that since there is a resistive force that the charge carriers inside of this wire experience, there is an amount of negative work that force will do on these charge carriers. In other words, that has the result of, I guess it's the result of, I want to word this. The presence of that frictional force means that some negative work is going to be done on that charge carrier. So that means that if we're talking about an ideal battery if we're talking about a practical battery as opposed to an ideal one, over time, the speed that this imaginary escalator can reach will change. And that's essentially why a battery dies, why it becomes incapable of producing or pushing charge at a rate that causes current in the circuit to be bigger than 0. I'm not talking about that case yet. In that case there, you'll see some context clue or something that refers to internal resistance. And in the absence of that, you can imagine that you've got an ideal battery so that it will work forever. The escalator will always be capable of pushing charge so that the current in this wire loop is greater than 0. It's not working like against an additional force to cause these charges to climb up the escalator. And we can say for sure that the amount of current that the battery is producing is going to be equal to the EMF. So the delta V, or the potential difference between the terminals of the battery when the battery is not actually doing a job, divided by the resistance in the circuit. And I feel like this is something that's a little bit easier to demonstrate with a practice problem coming up. So put a pin in that idea, and if after we see our practice problem, some of it is still shaky, jump in on the chat or on the mic at any time. So I mentioned earlier that there are different classes of materials for which resistance is a constant no matter what amount of current is moving through that resistor, or when that resistance value changes in response to the amount of current that is that's moving through it. And there's terminology for this. So ohmic materials are the ones for which there's always a one-to-one relationship between the current that's going through them and the delta V that's sort of responsible for producing that current. So if I were to take the slope of this here, I wouldn't get the resistance directly, but I would get 1 over the resistance as the slope value. So that means that the resistance is just going to be the reciprocal of the slope. It also means that there's no reason I couldn't plot delta V versus I as opposed to I versus delta V. And for ohmic materials, the any generic resistor that we talk about is going to behave this way. Our water tubes that we worked with last week are closer to being like a perfectly ohmic material as opposed to one that's non-ohmic. And then other conductors, these are materials that have a large number of, a large number of available valence electrons that can move throughout the interior of that material so that they have a sea of electrons that can freely shift. So things that conduct the flow of charge based on our definition from back in chapter 22. So for non-ohmic materials, there is no longer a one-to-one relationship or one-to-one ratio between the delta V that you put across the ends of this resistor and the amount of current that you can measure going through this resistor. And batteries being capable of increasing their internal resistance over time, that means that they're also non-ohmic. If I have a battery that I connect in, let's say, a flashlight circuit, and I leave that flashlight on forever, we know eventually that battery is going to fail to be capable of causing the light bulb to light. That means that over time, its internal resistance is changing from something that is nearly zero to something that is a larger magnitude positive. So if we were to increase the delta V across our, and I guess what's really going on here, if we want to think about how a battery behaves, we would imagine that a fresh battery right out of the pack has a delta V between the terminals that is the same as its EMF. So when I say delta V between the terminals, I specifically mean when that battery is actually on and doing a job. We learned in chapter, our electric potential chapter, I think, we learned that the EMF for a battery is the same value all the time, whether it's fresh out of the pack or if it's dead. So when it's fresh out of the pack, the delta V is going to be about the same as the EMF. But over time, the actual delta V, what you actually get out of the battery, is going to get less and less. And as the delta V between the terminals of the battery gets smaller and smaller, the internal resistance in the battery is going to get bigger. So the current that it's capable of producing is going to get smaller. So like T is equal to 0 for a battery fresh out of the pack would be over here. And then over time, the amount of current that that battery would be capable of producing would trend towards 0. And it would get to the point where it was not powerful enough. And when I say it was not, imagine that I'm talking about the imaginary internal escalator. It's no longer powerful enough to overcome the frictional force that those charge carriers experience. So it's as if the escalator switches off. It can't lift charge anymore. A capacitor works in a similar way. If you think back to, see if this diagram is in this half or not, but we had a pretty good illustration that showed why this should be the case as well. I guess we can, yeah, I guess this would be our best bet here. So this slide, we used this to kind of illustrate how the law of conservation of current dovetails with the junction law. There are no junctions anywhere in this circuit, so an electron that starts off on the negative plate of the capacitor has no choice but to go through light bulb A and light bulb B. So if there are, imagine there's an ammeter in this loop, and we start off with a charged capacitor. We, let's say, close a switch so that this capacitor can start to discharge. The amount of current that we would see in this wire would not be constant because as the capacitor goes from being fully charged to uncharged, it is moving charges at a different rate or a different speed. So imagine our capacitor 1 second after we close the switch, and imagine how quickly these negative charges would be trying to rearrange themselves throughout this circuit. And then imagine 1 second before these light bulbs shut off. So 1 second before the current actually goes all the way to 0. There has to be some sort of deceleration that we would be able to measure if we were tracking a single negative charge as it goes from the negatively charged plate toward the positively charged one. Because these light bulbs won't light forever, the capacitor is either charged or uncharged. And when it's in the process of discharging, it's pushing charges at varying speeds, or I should say from one moment to the next, the velocity of any one charge changes. So we wouldn't expect to get a constant current if we could plot delta V as a function of, or I should say it this way, we wouldn't expect that the resistance in this circuit would read as a constant because the delta V and so the delta V between the plates of the capacitor would be trending towards zero. The current would also be trending towards zero. So for that reason, we can think of capacitors as being examples of non-ohmic materials. And I think the last one in our list was diodes. We are not really going to get a chance to work with diodes until the very end of the semester. Our last experiment is going to involve verifying the photoelectric effect using diodes that have different colors, thus different wavelengths. And as we can see here, they will respond to current in different ways. So this is, if anybody's interested in seeing some of these when we're in lab this week, let me know and I can pull some out and set them up. But these are also materials that act as if their resistance values are different for small currents, which are the result of small delta V's, or they're different compared to what we see for large currents, which are the result of larger delta V's. So instead of having just a capacitor and a wire, or even just a battery and a wire, in practice, if your goal is not to just short circuit your battery, you would need to have some amount of resistance or some load that has a large resistance compared to the internal resistance of your system to begin with. And since we've got an EMF symbol here, it's okay for us to treat this battery as if it is ideal, so that the delta V that I would measure between terminals when the battery is actually on, when it's actually doing a job, would be the same as whatever is printed on the outside. So if we treat this as like a C battery has got a potential difference of 1.5 volts between terminals. Now, the wire that we use to connect either the positive terminal to the negative, or as is the case here, to wire up our circuit with our generic resistor, it can be optimized, or we can optimize the electron current inside of this material or inside of the specific wire by just being clever about the material that we choose to build that wire from. But the wire is never going to have zero resistance because the resistivity of this wire is never going to be zero. So there is a small amount of resistance that we would be able to attribute just to the wire segments here, whose job are really just to connect the dots, to give the negative charge carriers somewhere to go. But compared to the resistance of this load here, the resistance of the wire is going to be very small compared to the resistance of the load. So what this means is that if we could measure the potential difference between, let's say, the terminals of our battery, and let's pretend it's a C battery so that we get 1.5 volts between here and here. If we measured the potential difference between the ends of the resistor, we would get most of that 1.5 volts. So it might be like 1.48 volts or something, where the remaining 200ths are something that we could attribute to the wire segments themselves. So there's no way to actually idealize the wire so that there's no resistance whatsoever. But our goal is for the delta V across the wire to be really small compared to the delta V across the terminals of the resistor, and thus the delta V across the terminals of the battery. So if we could take this resistor out, and I believe our next, I guess maybe one of our next 2 slides is going to discuss this here. But if we took this resistor out, then the delta V between the ends of the wire would also need to be 1.5 volts, just like the delta V between the terminals of the battery. And that would mean that a very large amount of current would move through the wire because there's a very, very small amount of resistance to oppose it. So this would be equivalent to the imaginary escalator on the interior of the battery speeding up so that it's moving incredibly quickly. And that process would cause the battery to deplete at a faster rate. So this is the scenario where you short circuit a battery by forcing it to produce a lot of current in a small amount of time, or over a short window, I should say, because you've built a circuit that has almost no resistance in it. Oh, and this point here that I don't want to gloss over, if we think about this from both a law of conservation of charge perspective and a Kirchhoff's junction law perspective, there are no junctions that give a charge carrier that's moving out of the positive terminal of the battery the opportunity to go anywhere else. So the amount of current that the battery is producing has got to be equivalent to the amount of current that's moving through the wire at any one point in time. That also has to be exactly the same as the amount of current that's moving through the resistor at any one point in time. So if I had an ammeter and I put it between the positive terminal and the top of this resistor, I would get exactly the same current value as if I moved my ammeter to the lower part of that loop. So now here, so we're still okay in the chat. Jump in at any time if you have questions. So now here we can see the difference between the potential difference at any one like physical location in an idealized circuit compared to a practical one. So the unit on this x-axis is purposefully vague. Imagine that this x-axis is just telling me or it's something that I can interpret as the length of the wire. So that any charge carrier that starts off near x is equal to 0 and then makes its way toward x final or x maximum, whatever that may be, that charge carrier has given up all of its electric potential energy as it goes from end to end. So we can imagine that this end of the wire in reality just connects back to the negative terminal of the battery so that a charge carrier that's lost all of its potential energy can hop right back on the imaginary escalator and be lifted up so that it has more potential energy and your light bulb or whatever that's in your circuit stays consistently lit as opposed to kind of blinking off and on. It's just a continuous process. So the delta V of the battery is going to determine how much potential energy that charge carrier will have when it moves out of the positive terminal of your battery. So whatever that delta V is, by the time the charge makes its way up the imaginary escalator, it has moved through the entire potential difference of the battery. And for an idealized circuit, the potential difference across the wire segments that connect us to the resistor are exactly 0. We know that that's not really practical, but for an idealized circuit, it's okay to assume that the entire delta V is attributed to the resistor. None of it is, and I should say resistor or resistors, because we're going to pretty quickly start practicing with more than one resistance element. But we can assume that all of the delta V is due to the resistor or resistors. None of it is attributed to the wire. And in reality, if we had taken the delta V between, let's say, the wires that connected our power supply to one end of the conductor, our saltwater tube, and then compare that to the delta V between the far end of the saltwater tube and the opposite side of our power supply, we would find that there was a very small but not 0 potential difference across the wire itself. So in reality, the shape of this voltage versus position graph would be really similar for the practical circuit and the idealized one. However, the slopes would be very slightly different. They'd be very slightly larger in magnitude for the wire sections of the circuit and very slightly smaller in magnitude for the resistance value or the resistance portions of the circuit. So the idealized one is assuming that all of your delta V comes from the resistors. Since in reality, most of it comes from the resistor, but not all of it, this slope segment would be a little bit smaller in magnitude. Okay, so let's put this into practice. The current through a wire is measured as the potential difference delta V is varied. So imagine that you have your same setup from last week's lab, but instead of paying attention to the voltage when it's or the potential difference when it's exactly 1 volt or exactly 2, if we were concerning ourselves with what happens when you turn the dial. So what is the wire's resistance here? So this resistance value, since this is something that we can model as being ohmic, we have a good idea of what its current versus potential difference graph will look like. We know that this slope is going to be linear no matter what. So as you cause the potential difference to get larger and larger, you are not changing the resistance of the wire. You are instead changing the amount of current that goes through the wire. So if this is our graph here, we can compute the slope of this. So 50 amps divided by 1 volt, 50 amps per volt. The reciprocal of that will give me the ratio of volts per amp. And that is what we can associate with the resistance in ohms. So if we have 50 divided by 1, that's going to give us the slope. So the resistance is going to be 1 divided by 50. That's how we get 0.02 ohms. And this is reasonable, even for a fairly large current. And when I say fairly large, it's one that's going to be large for any of the experiments that we're going to carry out in lab. But as we get like toward the end of this unit here, we'll see that there are some benefits to, I suppose, moving electricity from one place to the next at very large currents, but small delta V's, and then vice versa. So for the time being, just think about where the electricity that you're using right now was actually generated. I'm guessing nobody actually lives at a power plant, so there has to be some process that's kind of creating electricity at some far distance and then dispersing it over a much larger area. And if we think about that trip between your, let's say, nearest power station to like your nearest substation to the nearest transformer near wherever you are right now, there are some benefits to either scaling up the current while making the delta V relatively small or doing the exact opposite. And what you are trying to achieve in playing around with those current and voltage values is you're trying to minimize the impact that this wire's resistance has on the amount of electricity or the amount of energy that you're moving from one place to the next. So to just kind of go back to this scenario here, in our practical circuit, the length of the wire between your nearest power station, or your nearest power plant, your nearest substation, your nearest transformer, and then to wherever you are right now, that length of wire, that adds up once they get very large. So if we want to make this slope segment as close to horizontal as possible, with the reality that it's never actually going to be legitimately zero slope. But if we want to minimize this, we want to minimize the delta V across those very long wire segments, separating the power plant from wherever you are right now. And as we can kind of model, if wire is something that we can model as being ohmic, if we want a really small delta V, but R is going to stay the same value, we also want to minimize the amount of current that's moving through that section of the wire. And we haven't yet talked about power from an electrical sense, but just from our knowledge in semester 1, we know that power is either the rate at which energy is used per unit time or the rate at which energy is being produced per unit time. So if we want to minimize the power loss that we would experience over that long trip that takes energy from, or takes electricity from the power plant to wherever you are right now, then it would be in our best interest to shrink the current as small as we can possibly get it, because that means that the delta V is going to be as small as possible for that trip. And I'm getting a little ahead of myself because transformers are something that we won't be ready to attack until we've had some more discussion about magnetic fields. So that's coming up later on in this unit, but that is the same type of real life consideration you would need to take into account if it was up to you to determine how to deliver electricity over long distances. Okay, so for a more simplified or a more realistic scenario here, let's imagine that we have an ideal 9-volt battery that's connected to some resistor. We don't know what its value is, but we can put an ammeter in this circuit and find that we have 60 milliamps of current. If we wanted to figure out what this resistance value would be, and we are again assuming that this is an ideal battery so that we can say that the delta V between the ends of this wire segment, whose only job is to connect the dots, really, to give the electrons a place to go. The delta V across that wire segment is going to essentially be zero. So the whole delta V of the battery should be reflected across this resistor. We can use Ohm's law here. We can rearrange it to solve for R. We have two kind of externally measurable quantities. Delta V can come off of a voltmeter. The current can come off an ammeter, just as we worked with last week. So this ratio of 9 volts to 0.060 amps is going to yield a resistance value of 150 ohms. Okay, that's the end of this chapter here. Let me take a look at our next chapter real quick. But before I do that, I want to hop on our mastering page just to make sure that everything that should be open is open. All right, I can fix that. All right, so looks like I've got one that should have opened for chapter 30, the one that we just finished. So I'll open it now and then schedule it for 1 week out from today, since you didn't have the chance to work on it Friday or Saturday. So if today is the 25th, 1 week out will be the 1st. And it's not going to show up on Canvas immediately, unfortunately, but if you go to the MyLab and Mastering tab and then follow through and open Pearson that way, you'll be able to see it immediately. Okay, so that is fixed there. Let's take a look at chapter 31. That'll give us a chance to actually do some problem solving, which I think makes it a little easier to kind of gain some confidence in these relationships, because they are sort of deceptively simple in a lot of ways. There we go. There are a lot of linear relationships that we're investigating in this unit. So they are going to generally be as simple as voltage is current times resistance, or power is current squared times voltage. Some of them are as straightforward as they look, even though it's kind of hard to convince yourself of that fact, because we can't actually watch electrons moving through a circuit, or we can't see what potential difference means because we can't actually see an electric field. But once you learn the rules, it's not really as hard to understand as it might seem. Okay, so this image here that we have up is kind of our cartoon image of a resistor, a battery, and then a parallel plate capacitor. And it's not going to be in our best interest to spend a lot of time sketching out circuits in this fashion. So we can kind of transition from this cartoon circuit diagram to now a traditional circuit diagram, where we've already had a chance to see what a parallel plate capacitor looks like in a circuit diagram. We have at least once seen what a battery looks like in a parallel plate, in a simple electric circuit diagram. And now we are introduced to the symbol for resistance. So any general resistor in a circuit diagram can be indicated like this. If we know that instead of just any old resistor, we're working with, let's say, a light bulb, or if we're working with an inductor or a diode, there are different symbols that you can use for those, but we're just going to start off with these generic resistors. I don't recall whether I mentioned it the first time that we saw a battery symbol in a circuit diagram like this, but a A battery, like a single cell battery, is one, or it has a symbol that looks pretty similar to what we saw for the parallel plate capacitor, only the lines that we use to indicate the battery do not have the same length. And in this case here, if you have like multiple sets of parallel lines as opposed to just one, we can interpret this as a multi-cell battery, where in all cases, the shorter of the two lines that makes up the battery symbol is going to represent the negative terminal of our battery, and the longer of those two lines represents the positive terminal. So if we just take a look at this image here and we imagine a charge starting off at the negative, at the bottom of our imaginary escalator at the negative terminal of our battery, when it has gained enough potential energy to get to the positive terminal, there's right off the jump, or right from the bat, or right off the bat, or right from the jump, there is a junction. So that a charge has the choice, or it has the option to either move through this left circle that takes it through the resistor and then back to the negative terminal of the battery. The rest will go toward charging up the capacitor. And that's what's indicated by this little, it's kind of perpendicular section of our circuit diagram. Some of the positive charges that we can imagine that are actually moving through this circuit, once they get to this junction here, some of them are going to continue on to the capacitor. The rest are going to go through this resistor here. And if I can find one junction that happens somewhere on like the, I guess the near side, or like the positive side of our battery, I should be able to find another junction somewhere else where these charges that split up will rejoin again before they actually make it to the negative terminal of the battery. And then we are already familiar with the EMF. It had been a while before today since we'd actually seen it in a, or since I had talked about it, I think, in a circuit diagram, but that's just our script E, not an epsilon, as the permittivity constant is. And then R and C represent resistance and capacitance, respectively. Okay, yeah, so just some more things I already stated about how you can tell the difference between a battery symbol and a capacitor symbol, and then the meaning of this script E, that's the EMF for the battery. Now, these different symbols, let's see, we've already seen the wire, the resistor, the junction, the capacitor. A light bulb and a switch have symbols that look like this. You might also be familiar with like a diode symbol, an inductor symbol, depending on, I guess, how much experience you already have with circuit diagrams. There are a bunch more symbols that you can add into a circuit diagram if you have just like, as opposed to just the bare minimum number of elements, which would be like a battery, wire, and some type of resistor. As you build more complex circuits, you can add all of these items or some combination of these items in addition to diodes, inductors, all sorts of extra stuff. But this is really all we're going to need in order to get our footing, at least in this first half. We're going to slowly make these circuits more and more complex as we learn more about the magnetic field and how it works alongside the electric field. So this here, I won't spend too much time on this because we already reviewed this a little bit earlier, but the junction law just indicates that the current that goes into a junction has to be equal to the amount of current that comes out. And this is really kind of just the law of conservation of energy combined with the law of conservation of current to kind of come to this conclusion here. If I have a certain amount of potential energy that a charge has once it enters into this junction, if I could track the potential energy loss that charge would experience if it took this path that's indicated by I3, it's got to be the same as the potential energy loss that charge would experience if it took the path indicated by I2. So there might be different amounts of resistance, different amount of wires. There could be different devices that are on the different branches of this circuit. But the one thing that I know for sure is that once a charge carrier goes through all of those elements, and then makes it back to the negative terminal of the battery, it had to have lost a very specific amount of potential energy. So from like that standpoint, the amount of energy, or like the rate at which potential energy is being lost along path 2 has got to be the same as along path 3. So we can think about the amount of energy going into this junction being equal to the amounts of energy that have to come out, and thus the amount of current that goes into that junction has got to be the same as the amount that comes out. So for this case here, we just have some generic currents, I1, 2, and 3. This section here, so I1 has got to be equal to the sum of I2 and I3. And there's no reason that I couldn't have named, or that Pearson couldn't have named these currents differently. And I should say this junction law statement here is something that you will have to build every time you look at a circuit. It's almost like net force, in that you can't always say that net force is, let's say, tension minus gravity. That simply doesn't apply to a lot of the problems that we, all of our popular crate problems that we worked with in semester 1. So there's not a single equation that will always give you or that will always tell you how these currents add together. You always really kind of have to start from the very beginning. Sum up the currents going in, recognize those have to be the same as the currents that are exiting that same junction. Now the loop law, I mentioned in our review kind of in passing, but now specifically relating this to a charge that's moving through a circuit, not just any old charge that's moving through space and coming back to its original position. If we can imagine a charge that is, let's say, delivered into, or that's put into this loop by a battery, and let's say that it's being maybe put into this loop is a bad choice, but imagine that we have a loop that involves 4 things. One of them is a battery, the other 3 are resistors. If I were to start right here in the upper left-hand corner, my charge carrier is going to gain potential energy as it moves from one terminal of the battery to the other. But from there on out, it's just moving through resistors, so it's going to lose potential energy. So the loop law here, if this is going to be equal to 0 in the scenario that I've made up here, I'm going to have one positive delta V that represents the field on the inside of the battery doing work on a charge, and specifically positive work on that imaginary positive charge. But if I imagine a negative charge that's moving toward the negative terminal of the battery, that would also result in positive work. So that would be energy that you're adding to the charge, regardless of whether you're considering electron current or conventional. And if we switch back, just for the sake of example, to conventional current, I have now a positive charge that's moving clockwise through this loop, and it's losing potential as it goes through each resistor. So let's imagine that our battery is a 9-volt battery. My charge carrier can undergo a potential difference of -3 volts, -3 volts, and -3 volts if all 3 of my resistors are equal to one another. If they aren't, it could be, let's say, 1 volt, 5 volts, 3 volts, anything that adds up to the total amount of positive potential difference that that charge experienced. So I have, some quantity of numbers, some mixture of positive and negative delta V's that when I take them all into consideration and trace that single charge carrier all the way through the loop, it's got to get back to where it started from. So when it's at the bottom of the imaginary escalator, it has lost all of its potential energy and is ready to have some work done on it so that it can go through the loop again. And this picture is kind of purposely generic. It almost implies that you could have 4 resistors in a loop and have some non-zero current without having anything like the battery or the capacitor actually triggering some current or producing current in that loop. But any one of these generic delta V's can be replaced with a charged capacitor or with a battery, or could be an uncharged capacitor. We can sort of fill in any of those elements in this loop here. I just find it personally easiest to imagine that one of these is a battery and all the rest of them are resistances. So if we were just presented with a circuit diagram, and we were asked to solve it so that we could figure out everything that there is to know about that certain circuit. There is a problem solving strategy that I would suggest that you stick to, especially if you are like new to solving circuits. Start off with a circuit diagram the same way that in semester 1 we would have started off with a motion diagram or a free body diagram for an object that we were trying to understand. Taking the description of your scenario and then turning it into something that you can interpret visually is incredibly helpful. If you know the direction of charges, the conventional current in that circuit, you can indicate it. But even if you don't know for sure, you can just make a guess. And there's a step later on in this procedure that will verify whether your guess was correct or not. And there are really only two options. If I have a wire segment like this, current can be heading in this direction or that direction. So if I guess that current is heading in this direction and I end up calculating a negative current value, all that tells me is that my initial guess was wrong, but I can still figure out how much current is traveling through that wire and the direction, because there are only really two options, forward or backward. So sometimes you will know the current direction, but it's not always a given. So it's okay to make a guess and then confirm later whether or not that guess was correct. Then we want to apply the loop law, just as we did in that example on the previous slide. So just to backtrack here, we were given a hint that we should go through this loop clockwise and that we should start and end at this position here. There's no reason we couldn't have done the opposite. There's no reason we couldn't have chosen any other start point in this loop and continued to go through clockwise, or we could have chosen any other starting point we wanted to and worked through counterclockwise. The direction of the loop is not something that is really important, but that is going to, I guess I should say, once you've chosen a direction, you have to stick with it. So it's important in that context. But it's sort of similar to our coordinate systems when we were talking about kinematics and dynamics in semester 1. There was not one ultimately correct coordinate system that made all the other possible coordinate systems incorrect. As long as you stuck with whatever choice you made in the beginning, you would still come up with a meaningful answer. And that is still true here. So choose a direction to go through the loop that you've determined in part 2, and then apply the loop law. So figure out where junctions are if they exist, track how the current heading into that junction compares to the current coming out of that junction. And then if you pair that up with Ohm's law, you can really tackle the simplest circuit to the most complex ones. And we're going to start with simple circuits to start with. But the discussion that we're heading into here kind of dovetails with one that we had when we were talking about capacitors in groups in the potential and field chapter right before our test. So we learned that if you had a single capacitor that was being charged by a battery, eventually the delta V for the capacitor would match the delta V for the battery. But that changed when you had more than one capacitor, because it mattered whether you had two capacitors in one loop with the battery or if each capacitor had their own loop. And in that conversation, we found that in one scenario, the amount of charge that showed up or that accumulated on each capacitor was going to be the same value, regardless of whether the capacitors were identical or if they were very different. And in that case, their delta V's would have to add up to whatever the battery potential difference is. And then there was another scenario that was essentially the opposite. I could have two very, very different capacitors, but if I wired them up so that they were in parallel with one another, that they had their own individual connection to the terminals of the battery, then their delta V's would be the same value. Q is what would change in that scenario. And we're going to run into some similar rules here with resistors. If I just have a single resistor and a single battery, this becomes really straightforward. But if I have more than one resistor, then I can end up asking that battery to produce different amounts of current, even though the battery resistor 1 and resistor 2 are all fixed values. So in other words, you can imagine that arranging your resistors in a specific fashion can actually control the speed of the imaginary escalator on the interior of your battery. So for our simple circuit, we've got our source of potential difference, and then we've got our really generic resistor that's just referred to as the load here. And I do want to point out these stripes. They're not arbitrarily chosen. In practice, you can determine what a resistor is or what a resistance value for a specific element is by interpreting the color code on a resistor. You wouldn't be required to either use a DMM to measure the resistance or to set up a circuit so that you can calculate a delta V, or you can measure a delta V and measure a current and then calculate the ratio. So depending on like the type, I guess depending on the experience that you've had, if you are heading into like the CSE program, or if you are doing one of the electrical engineering programs, then you might have already taken a circuitry course that has introduced you to this here. But if you're new to it, this red, purple, black combination would be my clue that that resistor is different than if I found like a green, red, blue, or something like that. So at a glance, you can tell what resistance is without having to put that resistor into a circuit. I can take this kind of cartoon circuit and turn it into my simplified circuit diagram here. And I think this might have been the first time that we've seen emphasis on the term complete circuit. This just indicates that I have at least one loop that connects the terminals of my battery to the resistance elements. If I could like take wire cutters and snap or cut this wire at any point here, I would not have a complete circuit anymore, because charge wouldn't be capable of jumping across the gap that I created by cutting the wire. So that just implies that I have at least one intact loop so that current can flow and that the imaginary escalator can be turned on. So if we go through our problem solving strategy, let's say we've got some ideal battery with an EMF shown here. I have some resistor here that's got a positive and a negative shown here that don't indicate that the resistor is functioning the same way as the battery. So in other words, we shouldn't take that to imagine that there's also an imaginary escalator inside of the resistor. We're just taking this sign as or these signs, I should say, as an indication of how the potential is behaving. So I have a positive potential on the positive terminal of the battery. I have a negative terminal on the negative. If I could trace a charge carrier as it was moving through this ideal wire, the potential value that's coincident with the positive terminal of the battery would be the same as what I would get if I measured on the positive side, or the more positive side of the resistor. And I emphasize that because resistors don't have charge on their own, but if current is moving through them, then just like the wire segments that we saw in our previous chapter, one end of that resistor will be more positive than the other, one end will be more negative than the other. So in this case here, I have just a single resistor. So the point that is closer, or the part of the resistor that's closer to the positive terminal of the battery is going to be the more positive. So when a charge carrier goes from positive to negative, my delta V is going to be a negative value across here, whereas it's going to be a positive value here, because I am, I guess maybe jumping the gun. I'm kind of assuming that the direction of current that I've guessed is going to be heading clockwise. And in this case here, my guess is a good one, because I'm just tracking the direction of positive charges as we imagine them moving through this circuit. If I have, let's say, multiple loops here, so that it's not necessary, and multiple batteries specifically, so that it's not necessarily straightforward as to what the direction of current in a specific loop is. Again, it's okay to guess. But in this case here, I do know that it's going to be clockwise. So the charge is going to have a more positive potential right as it's going into the resistor, a more negative potential right as it's exiting the resistor. So that delta V is going to be a negative. This delta V is going to be a positive. I can write an expression for the delta V across each of the elements in my circuit. In this case, it's real simple. The delta V for the battery is just going to be whatever the EMF is, positive, because I'm imagining that the battery is doing work on the charges that will cause it to raise up, well, that'll cause our positives to go up our imaginary escalator, but a positive force and a positive displacement give me positive work. I can say exactly the same thing if I switch perspective and try to evaluate what's happening to the negatives. Negative force and negative displacement will still result in positive work. So the battery's EMF is always going to be treated as a positive. Now here I have a single resistor, so delta V across the resistor has got to be equal to the the current through the resistor times the resistance value. And resistance is something that we can always treat as positive. And the fact that we know that this resistor has to take away, or it's got to counteract the positive delta V that the battery is contributing, that's where this negative sign comes from. And I know that the current here has got to be the same as the current that I would measure anywhere else in this loop. And that's just the law of conservation of charge. There are no junctions where a charge carrier could split and not move through resistor R before it makes its way back to the negative terminal. So my loop rule is going to be real simple. I thought it had an extra, like a number 4 here, but my loop rule would just be delta V total is equal to delta V bat plus delta V resistor. That's equal to 0. So in other words, I know that the magnitude of delta V bat has got to be equal to the magnitude of I times R. And it really is that straightforward for a single light bulb in a circuit. It gets a little bit more complicated, but still pretty understandable when you have more than one resistance element. And we're going to work with light bulbs here because we're going to see light bulbs in this week's lab. We have a chat question here. Let me go back a slide. So our question is, can you please explain again why the battery indicates a clockwise rotation? Because I only have one battery, I only have one source of positive potential difference in this circuit, then any charge that moves out of the positive terminal of the battery is only going to have one possible path. So this question, I think, is going to be a little easier to visualize and like a little easier to answer when we see a multiple battery circuit. But there's only one battery here. This battery is moving charge from its negative terminal to its positive terminal, and my current is such that this current, or excuse me, my circuit is such that this current would have to move through this loop clockwise. If I could flip the battery around, I would still predict, or I would still measure exactly the same current in this loop, but then my positive terminal would be down, so it would be like my escalator is moving positive charges down instead, and then it would make sense to flip the direction of that current to counterclockwise. But you should really just look at the battery if you have a single battery circuit with one or more resistor. It gets more complicated when you have more than one battery. Right, no problem. So let's look at our multiple resistor circuits. We're imagining that we've got light bulbs here, and light bulbs, I think they were not in our list of non-ohmic materials, but light bulbs are non-ohmic. So we're making an assumption here that the delta V for or between the terminals of our battery is going to be constant. Thus, the current that's moving through each light bulb is going to be the same value. I'm not going to imagine that I have a power supply whose voltage dial I can turn. Let's just say that I have a fresh battery right out of the pack, so that the delta V I would measure between terminals when this battery is actually doing a job is exactly the same as the EMF. So if I could trace the direction that a positive charge carrier would have, so in other words, if I try to identify the direction of the conventional current, it would be kind of similar to that single battery, or that single battery, single resistor case we saw in the previous slide. So both of these light bulbs would have, or I should say, their more positive end, or the positive side of each one of these light bulbs would be on the top. So in other words, if I chose a point right above light bulb A and then compared it to a point in between bulb A and bulb B, the charge carrier would have more potential energy right before it goes into bulb A. It would have lost some of it as it goes through bulb B, and then it would lose the rest, as it starts to go into bulb B, and it would lose the rest of its potential energy as it goes out of bulb B. So in other words, if this is a 6-volt battery and these light bulbs are identical, I would expect a 3-volt potential difference across bulb A. The remaining 3 volts would be across bulb B. Since there are no potential, or since potential is a bad term here, but since there are no junctions, there is only one path that a charge carrier could take. So I can say for sure that these two delta V's, the potential difference across bulb A added to the potential difference across bulb B, has to equal the potential difference between the battery terminals. And again, that's just the loop law compared or combined with the junction law where there are no junctions. So the delta V across bulb A and has to add to the delta V across bulb B to equal the delta V produced by the battery. So just as we indicated when we had our single resistor circuit, we can imagine our charge carrier getting some positive work done on it as it goes from the negative terminal of the battery to the positive, but then losing all of that potential energy as it works its way through the circuit. And since these are light bulbs, some of that potential energy is going to go into the kinetic energy of the charges. Some of it's going to go into the light that the light bulb produces, and some of it's going to go into the heat that that light bulb produces. For a resistor, just a generic resistor, it wouldn't produce visible light. But if you think back to the very beginning of our current and resistance discussion, when we were talking about indicators of current that you can use to determine whether current is present or not, let's say if you don't have an ammeter, you would still be able to feel a temperature change for a resistor that had some current moving through it compared to a resistor that had no current moving through it. And the behavior of a compass needle would still be able to indicate whether current was present or not. So I just want to point that out because we are talking about non-ohmic materials here. So there is a large amount of this potential energy that is lost due to thermal energy or the production of heat and the production of light. That kind of indicates, or that kind of backs up why light bulb filaments are made the way that they are. If you were trying to make a light bulb whose job was to produce a whole lot of radiant energy, you would want to choose a material that really resists the flow of charge so that there's a large amount of negative work done by the material in the filament itself so that you lose a whole lot of thermal energy. But the trade-off is that that object warms up and it produces light, which is, the light bulb's entire job in the first place. It wouldn't make sense to choose a light bulb filament that's made up of, let's say, copper or something that does a really good job of facilitating the flow of charge because you're not going to get that huge amount of radiant energy and heat, which is what you end up with a real life light bulb. So if we're imagining that both of these bulbs are the same, I know for sure that delta V across A is going to be exactly 1/2 the delta V between the battery terminals because delta V across B and delta V across A are going to be the same. There are no junctions, so the current moving through light bulb A is going to be the same as the current moving through light bulb B. That's going to be the same as the current produced by the battery. But we can come up with a way that, to combine these two resistances pretty similar to the way that we combined capacitance values in Unit 2. And this last point here, I just want to point out, the imaginary escalator inside of our battery is moving at the same rate the whole time. So it's not that current is decreasing as time goes on. It's not that current is increasing as time goes on. It's literally just the amount of negative work that the frictional forces on the internal to the light bulb filament provide. So that thermal energy is fed out of the system. You end up with a whole bunch of radiant energy and heat energy as a trade-off. but the escalator has to stay on the entire time. So it's got to continue pushing the whole time. If you could just move your charge carrier from the negative terminal to the positive terminal just a single time, then you would see a bulb that lights and then goes to darkness. You need the escalator, you need the battery to continue pushing. So when we talked about power for the first time in semester 1, we were just looking at it through a mechanical lens. So if we had, let's say, some object that was doing mechanical, or some force that was doing mechanical work on an object, we saw how that could change the mechanical energy of a system. And if we were, let's say, just limiting ourselves to conservative forces, so imagine there were no frictional forces that were acting on our system. We just had, let's say, a crate on a frictionless surface that is pushed a certain distance for a certain time. We could figure out what the final velocity of that crate was. We could use that to figure out what the final kinetic energy of the crate was. And we knew that we could balance that against the amount of work that the push did, or that the pushing force did, when we combine that force with some displacement. So if we wanted to determine the rate at which that object increases its kinetic energy, what we would need to do is kind of compare or combine our time independent energy conservation approach with our time dependent kinematic approach, so that the ratio of that energy production over delta T gave us a power in watts, where a watt is just a joule per second. We know that there's a joule embedded in the volt, because a volt is a joule per coulomb. And we also know that there's a time unit, there's a second, that is embedded in the definition of the amp. An amp is just a coulomb per second. And it's not immediately obvious at first glance, but if you can measure the current moving through some circuit, so in this case here, we're looking at the current produced by a battery that has some EMF that's shown here. The product of those two is going to leave us with an energy in joules divided by some time in seconds. So this power is also something that we can measure in watts, just as we did when we were just limiting ourselves to mechanical energies. So if we want to think about what has to be happening on the interior of the wire that is receiving some current because it's connected to some battery, we already know that the direction of the force that's acting on the negative charge carrier is going to be anti-parallel to the direction of the electric field. So we have our electron current that's tending toward the left, conventional current that's tending toward the right. The amount of energy that any one of these electrons starts off with as it kind of undergoes all of these elastic collisions with the positive charges that are in the lattice, that's going to change over time because of the internal frictional forces that are present in the wire. So in other words, if you leave let's say you have a flashlight circuit, you turn the flashlight on, the light doesn't become increasingly bright. So the amount of potential energy that the charge carriers pick up as they go from the negative terminal of the battery to the positive, it doesn't accumulate. It's always being dissipated somewhere in the circuit. So by the time that same charge carrier gets back to the negative terminal, it needs to go back up again. It's not adding any potential energy to what it had the last time around. It's lost all of that potential energy from its previous cycle through the circuit. So if our battery is continuously producing energy at this rate here, I have to be able to find something on the other side of that current that matches the rate at which energy is being dissipated by all of the resistance elements in that circuit. And this is how we can apply that same logic to the resistance elements that exist in your circuit. So again, the light and the heat that come from the light bulb filament are a form of thermal energy. It's the type that can enter out of your system, but you can't harness it in any way to feed it back into the mechanical energy of the system. It goes out without being capable of coming back in. So if you have the rate of change, like the first derivative of that thermal energy with respect to time, what you are really tracking is this quantity here. So dq dt times delta VR, because the potential difference across the resistor we're talking about, that's going to be a constant. But the rate of change is something that we can ultimately kind of trace back to how quickly the imaginary escalator in the battery is working. In other words, how large the current is going into that resistor. So if dq dt is just another way of saying current, if we can measure the current going through a resistor with the delta V across that resistor, that is going to be the energy dissipation that's balanced by the amount of energy that the battery is putting into the circuit. Again, this is just kind of like the law of conservation of energy again. If we take a look at this middle term here, dq delta V, or dq dt times delta VR, we know that the potential energy that this charge carrier is going to lose in this case, because we're looking at the resistance side, it's going to be something that I can balance against the amount of potential energy that that charge picked up from the battery. And way back when we were first talking about that charge escalator model, we saw that a single charge carrier that was pushed through some potential difference, delta V, would gain some potential energy, capital U. And that potential energy is what we are balancing against the thermal energy that's being dissipated by this resistor. So here we've got a combination of two kind of familiar elements. We have the current and the potential portion of Ohm's law. If we multiply those together, we end up with a power. And if I go back a slide here, if we were looking at this from the battery perspective, I have exactly the same relationship. Current times potential difference gives me power. So what if you were trying to figure out how much power was being dissipated across a resistor, but you didn't have access to a voltmeter? Let's say you had a resistance value that was maybe stamped on the resistor that you were working with, and you had an ammeter so that you could measure the amount of current that moves through it. We can take Ohm's law, so we know that this delta V across the resistor has got to be equal to the product of the current through the resistor and the resistance value itself. We can go from this expression up here at the top, where I is equal to delta V, and recognize that that's also saying that I is equal to that P is equal to I times delta V. That's also equal to P is equal to I squared times R, where now I have a way that's just dependent on current and resistance to determine the power dissipated by some circuit element. I can also evaluate that same property. Let's say I don't have an ammeter, but I do have a voltmeter and I know the resistance value. Then delta V squared over R will also give us a power in watts. And it's a little easier to see once we start like the problem solving stuff here. We can kind of go through how these units cancel out and actually like validate or justify, confirm that we do have the same power unit that we worked with in semester one. The source of the potential energy is the only thing that's different here. Okay, so let's imagine that we are trying to combine light bulbs here so that we can determine an equivalent resistance, kind of similar to the equivalent capacitance that we talked about in our second unit. So let's imagine we've got identical batteries, 3 identical bulbs. One circuit is just one bulb, one battery. The other one is one battery, 2 bulbs. So these batteries have escalators that are exactly the same height. So in other words, they can raise a charge through the same potential difference so that the charge is gaining exactly the same amount of potential energy in the circuit at the top as it is on the bottom. However, we know that the delta V that is, or I guess like the total resistance of the circuit, controls the rate at which the escalator is moving. So you can imagine that one of these batteries has an escalator that's moving quickly. The other one has an escalator that's moving more slowly. And you probably have a sense for which one is which, but let's talk through this step by step. So if I wanted to measure the potential difference across bulb A in the upper circuit, I know to expect that that should be the same as the potential difference across the terminals of the battery itself, because there's nothing else in that circuit except for wire. for this circuit down here at the bottom, if I were to measure the potential difference between or across bulbs B and C together, I should also get the same potential difference as the battery. What's different is if I were to measure delta V across bulb B by itself or bulb C by itself. I know that either one of those individually is going to be less than the delta V of the battery. And since light bulb A gets the entire potential difference of the battery, light bulb A is going to have a larger delta V than light bulb B, and it will have a larger delta V than light bulb C. So if we want to visualize which of these circuits is going to produce a light, or which one of the light bulbs in these two circuits will be brighter, what we want to look for is the one that has the larger amount of current passing through it. So the amount of resistance in the lower circuit is going to be larger than the amount of resistance in the upper circuit. So that means that the amount of current in the lower circuit is going to be less than the upper circuit. So bulb A should be the brighter of these three. Bulb B and C should be a tie. If we want to break this down in a way that's similar to what we did for our equivalent capacitance in the previous unit, we can, again, just look at one segment of a circuit with the assumption here that points A and B have different potentials. Otherwise, this current would be zero as opposed to non-zero. So imagine that there's a battery or a power supply, or something that's just not shown here that's producing the delta V that we're calling delta VAB. So across both of these resistors at once. There's no junction anywhere between resistor 1 and resistor 2. So I know that the current through resistor 2 has to be exactly the same as the current between resistor 1. Now their delta V's, or like their resistance values, can differ. And if we assume that they are different here, then our loop rule is going to involve our one positive delta V. So our battery that is not shown here but has to exist in order for the current to be bigger than 0. Then I have a negative delta V across resistor 1, another negative delta V across resistor 2. And once we get back to our starting point in the circuit, we are going to have a total delta V of 0. So in other words, we have traced through one complete loop, no more, no less, so that we know that these three delta V's add up to 0. If I know that the current through resistor 1 can't be different than the current through resistor 2, then I can factor out this shared current and just combine these two resistance values so that I have this EMF, which is a constant, multiplied by this current, which is a constant, times the product of these two resistances. So that means that if I can find a third resistor that has a value that's equal to whatever R1 plus R2 is, if I connected that to the same battery and let's say put an ammeter in that circuit, the battery would not be able to tell the difference between powering this circuit that's got this resistance value RAB and the one that we saw in the previous slide, which is the same amount of resistance but divided across two individual resistors. So if I want to quantify the equivalent resistance, so if I want to predict what the value of that third resistor that will cause the battery to behave identically, if I want to figure out what that should be, I can start here from an Ohm's law standpoint and just apply it to this one section of the circuit. And that's what can be so powerful about Ohm's law, is that you can apply it to a circuit as a whole and you can apply it to pieces of a circuit. And here we're just looking at the pieces of the circuit, so the combination of R1 and R2. I know that that delta V is going to be exactly the same as what I would measure if I had a voltmeter and I just touched it between points A and B. So I can replace the numerator here and I end up with I times R1 plus R2 divided by I. So the R1 plus R2 is all that survives. And I end up with a rule here that is opposite what we saw for series capacitors in Unit 2. In that case, we saw that capacitors in series added together as the reciprocal, or the sum of their reciprocals. Here, if you have resistors in series, they add together directly. So if R1 is 1 ohm and R2 is 2 ohms, RAB would be 3 ohms. So just in general, just as we saw with our series capacitors, there's one quantity that adds up to something else, some total value. And then there's another quantity that's the same everywhere. And for a series loop or a circuit that has series resistors in it, here we're imagining we were working with light bulbs, but this could be any old resistance value, RA and RB. There are no junctions, so that means the current is the same everywhere. If the current's the same everywhere, then the potential difference across each bulb is going to be that shared current times whatever the resistance value is. So if RA and RB are equivalent, then I know that delta V across bulb A is exactly the same as delta V across B. And I would know that delta V across either one of these bulbs would just be half of the battery voltage. If I had 3 bulbs in series like this and they were all identical, then I know my delta V would be 1/3 of the battery voltage for each bulb. But as long as you've got more than one bulb, your delta V's are going to add to the battery voltage, but the current is the same everywhere. And the equivalent resistance is just going to be determined by adding together the resistance values. We're going to see in our, we're just about out of time here, but we'll pick up on Wednesday morning with parallel circuits so that we can see how these same 2 light bulbs would behave if I connected them to the same battery, but in a fashion that gave each one of them their own connection. So this is something that you can always relate back to Christmas lights. Those are, if you think about like the old style Christmas light, where if one bulb went out, you had to go through that entire string to figure out which one was bad. And then once you replaced it, the entire string lit back up again. So each bulb relied on all the other bulbs in order to light. The same thing is true here. If I disconnect bulb A, bulb B has no connection back to the positive terminal of the battery. So bulb A relies on bulb B the same way that older style Christmas light bulbs relied on one another. And as we'll see with our parallel setup, that's going to be something that's eliminated. So just to give us a taste of what we're going to be working on Wednesday, these 2 bulbs, A and B, they don't rely on one another. So in other words, if I take bulb A out, bulb B is fine. It still has its own connection to the terminals of the battery. I can say exactly the same thing about removing bulb B. So these are more akin to the more modern Christmas light, where worst case scenario, you might get a chunk of the string that goes out, but you can lose one bulb without the entire thing going. Okay, I'm a little bit over. I apologize for that. Let's see. There's a private chat question I'll deal with after we're done. So just hold on there. Does anyone else have a question or concern that they want to ask before we wrap it up for today? Okay, if not, I think I need to publish the lab for this week. So that'll be done once I get out of lecture, my next lecture coming up. So check around like 12 p.m. or 1, somewhere in there. The next one will be up for this week. Otherwise, I hope everybody has a good rest of their day. And I will see you again either tomorrow or in lecture on Wednesday.